All right, guys. So we have a new chapter, chapter 21, and this is going to be on electromagnetic induction. So you can think of this as an application of the magnetic fields. And some of the things we're going to basically study in this chapter is Faraday's law and Lenz's law. So those are two laws that are related to one another, basically describing more or less same thing, where Faraday's law describes the mathematical view of the same, induction concept, and Lenz's law is, conceptual way of looking at that. We also have a couple of other things. We're going to look at what we call electromotive force and look at, new type of, let's say, a voltage source, which we call motional EMF. And at the end, we're going to look at, some of the application of the, let's say solenoid in a circuit. So we're going to look at some of the things, that are, mutual induction or self-induction. So if you put a solenoid in a circuit, what will you see? All right, so let's look at then some of the introduction to this particular chapter. And one thing I do here is I take few things from chapter, let's say chapter 22, and include in this in this particular chapter. And chapter 23 here is then later on when we look at it, it's going to be very short chapter. Sorry, chapter 22. And, basically I am looking at some of those things, pretty much included here. All right, so again, one of the things we have here with this, concept of induction is that this is an application of electromagnetic, or, you can think of like magnetic, forces. And the concept that we looked at in chapter 20 was basically describing how you can find a magnetic source from electricity. Remember, if you have a current running through a wire, it can act as a source for magnetic fields. Okay, and that means you can say that electricity generates magnetism, and that was true again whenever you have a wire with the some kind of conducting wire with the current running through that, and it generates magnetic field right around it. And other question that some of the let's say scientists wanted to ask during this time is the reversal also true? Can you use then magnetism basically to get electricity? And we have Faraday and Henry and Lenz, right? So those are some of the scientists that did a lot of contribution in this field. That means finding the way of generating electricity from magnetism. That means magnetic effect or a magnet or something like that can generate electricity as well. Okay. The only thing here is we're gonna see that there's a little bit of differences in terms of how you can get electricity from magnetism, and that's what we're gonna see when we go through the experiments that, let's say, Michael Faraday went through. By the way, Michael Faraday, he's a fascinating character, and is one of my favorite scientists, and I recommend you guys to kind of read some of the things about him, like let's say his biography or something like that, because he's really someone who had let's say very little let's say mathematical background, but was able to become an exceptional experimentalist, and basically do an experiment or set up an experiment or have a sort of like experimental insight, even though again he didn't, probably some of you have even better mathematical background that he does, but he was able to conceptually understand all that physics behind electricity, magnetism, and things like that. So some of this experiment he did was he was able to really see the relationship between electricity and magnetism, which later on we're going to see that Maxwell took some of this let's say his discoveries and put it in mathematical form. So we're going to see that, let's say, this Maxwell's equation, right? But technically Faraday is the sort of like the person who discovers that contribution from magnetism to electricity. And for example, in this picture, you can see that you have a person who's swiping the credit card. And this is something you guys do every day. Well, one of the things we have here is that that's application of the Faraday's law. That means, every time you swipe your card, there is a magnetic strip, right, on the credit card. And every time you swipe it, it generates electricity. Otherwise, it doesn't, right? But only when you swipe it, it does. That means one of the things we have here is that if you put your card over there, and I'm not talking about the one that has a chip, the one that kind of uses the strip. So if you just put it there and leave it there, nothing happens. You have to like move it quickly, right? Let's say swipe it so that, something happens. And that's because of the discovery of the Michael Faraday. All right. So then let's see some of his discoveries, basically. So we're going to do some experiments, or we're going to, look at some experiments that you can think of, like, were done by Michael Faraday, or very similar to Michael Faraday experiments, in order to understand what are the conditions for, generating electricity. Okay. So let's look at it. So again, you can see right around 1830s, that's when, some of this experiment and discoveries was done. So we have Michael Faraday. Again, his goal was to find how you can generate electricity, which is, current, right, from magnetic, source. And he took one of the magnetic sources, which in this case, a bar magnet, and he wanted to see, okay, so here's the bar magnet, and here's some kind of, a coil of wire. So this coil of wire is not connected to anything. That means it doesn't have any other power source. So what you see here is that there's a galvanometer. So this guy that is connected, so you can see, right? So here's the one end of the wire, here's the other end of the wire, and it's connected to a galvanometer. This guy just measures the presence of a current. That means if there's a current in the wire, right, in this coil of wire, this, the meter, right, galvanometer, will, detect it. Okay, it's not a power source. It only detects if there's a current or not. Okay, so let's look at, let's say first experiment he did. First experiment was, okay, so you have a coil of wire connected to the galvanometer, and then he holding a magnet some height above the, this coil of wire. And the galvanometer reads 0, okay? Galvanometer reads 0. That means, if you're holding a magnetic source, technically there is a magnetic, a source, right? There is a magnetic source, but there is no current. Now let's see what's going on when you're holding a magnet like that. Remember, magnetic source generates magnetic fields. That particular bar magnet generates magnetic field. Well, the magnetic field, remember, goes from north and comes back to the south. So technically the idea here is this. So there is a magnetic field going through the center of the coil, right? Basically through this area of the coil. So there's a magnetic field going down, right? And then coming back up, right? But outside of the coil, right? And goes into the south. But this is kind of the direction. That means there's a downward magnetic field through the, coil of wire, okay? So, but even though there is a magnetic field through the coil of wire, okay? So there is no current. That means meter stick, or the meter, right? That galvanometer doesn't detect any, any current. Okay, that means one conclusion here is this. When the nearby magnet is stationary, the meter shows no current, because that's what we're doing, right? We're holding a magnet, and by just holding that bar magnet, we have a magnetic field, and magnetic field going through that, a coil of wire. But if magnet is stationary, right, the meter shows no current. Okay. All right. So obviously the next thing will be for the experimentalist is to observe what happens if you have a moving magnet. Okay, since the stationary doesn't do anything. Well, one thing he discovered is that if you start moving the magnet relative to the coil, okay, remember the coil is just sitting there, but now you're moving magnet. By just moving magnet down, he was able to see there is a current in the wire. That means you can see, right, the needle is no longer shows 0 current. So that means there is a detection of the current. That means if you take the magnet and start moving toward the wire, right, toward that coil of wire, there is a current in the wire. Okay, so then this is what happens, let's say if it's going down. And then one thing he did here, he started moving up in opposite direction. Well, what happens here, it doesn't really show, but let's say then in that case, the needle in the galvanometer start pointing in opposite direction. That means it still detects current, but there's a reversal of the direction of the current. That means if you move it up or down, that means moving toward the coil of wire or away from coil of a wire, there is a current. Okay, now we call this induced current, right? We call this induced current, and the corresponding EMF required to cause this current is called induced EMF. Remember, one of the things we have here is that if there is a current, that means there is technically a potential difference between those two ends, right? That means there is an EMF. So the EMF is proportional to current. You cannot have one without the other. Okay, if there is a current, there is an EMF. So I'm going to put like IN, which means induced, right? So one of the things we have here is if you have a moving magnet near a wire or coil of wire, right, like that, you get a current in that wire. And the direction of the current changes, right, if you're moving toward the source or away from the, or, toward the coil of wire or away from that. Okay. Now let's see what happens technically then, when we're moving the wire, when we're moving the magnet. Remember that I told you that there is a magnetic field. Now let me give it, have a different, color. Like this. So think like this. So there is this magnetic field. Okay. Remember, magnetic field is down, right, through that center of the coil. Okay. So there's downward, right, magnetic field. Well, one thing I can do here is, so for example, if I come back here, right, see if there is a magnetic field, I can see that the strength of the magnetic field, for example, right, if I find the strength of the magnetic field here, that's this point P, right? So let's say that point P. One thing I can have here is I can, measure the magnitude of the magnetic field with respect to how far away it is from the source, okay? And I can calculate the magnetic field. But remember, since the source is stationary, right, in this first slide, right? So you can write 1 out of 4. If the source is stationary, magnetic field, everywhere inside, right, is the same. Now, 5 seconds later, 10 seconds later, 15 seconds later, right? 1 minute later, that means it's a uniform and constant magnetic field. It's not changing, okay? If your magnetic field through the coil of wire doesn't change, you have no current, no induced current. But here's then what we get. When you moving the magnet, relative to that coil, you can see, right, you moving the magnet closer and closer to the coil. That means, let's say if I'm finding the magnetic field somewhere over there, right? So let's say somewhere at the center of the coil. All right, so let's do this color. So if I'm looking magnetic field there, then what I have here is that as it's getting closer and closer, the magnet getting closer and closer, right? Well, magnetic field strength is increasing, right? Because closer the magnet gets to the coil, stronger the magnetic field inside the coil, okay? Well, as soon as I have that, I get a current. There's an induced current. That means there's a current in the wire. Well, if I move the magnet away from the coil, what happens? Then if I'm moving, then magnetic field, let's say, would decrease, right? Magnetic field would decrease. So this is when it's, moving away. And this is when it's moving toward. That means you get increase in magnetic field strength inside the coil when it's moving. So there you get a current. And when you're moving it away, right, then magnetic field decreases. And again, you get induced current. So that's why one thing we do here is this is known as an induced current, because that current in that coil of wire has it has no, let's say, other, let's say, potential source, no voltage source, no power source other than that bar magnet. That means that current that generated in the coil and, let's say discovered or, let's say recorded by the galvanometer is simply because the magnetic field inside the coil changes its magnitude. Okay, that means it's increasing or decreasing. That means you're changing the magnetic field through the coil. It generates current. Okay. All right. So how about different experiment? That means what he discovered here is this: if you change the magnetic field inside that coil due to the bar magnet, then there is a current in the wire. Okay, so how about if it's a different type of magnetic source, like let's say a magnetic field generated by a wire rather than by a bar magnet. So now he has another circuit. So think like this. So this is a second circuit. That means you have a coil of water, right? So let's say, so this is this, you can think of like, let's say this is first coil, and this is, let's say, the second coil. Okay, so the first coil is our original coil, and you can see, right, it's not connected to anything but galvanometer again. Okay, but the second coil is connected to a power source. So this is a battery with plus minus. There's a current, there's a battery, and if you connect that second coil to the battery, there is a current running through that. There's a current running through that. Well, what happens when there's a current running through some kind of wire, right? Some kind of conducting wire? Well, there's a magnetic field. And you can see, right, as there's a magnetic field, there's a current going through this wire, right? It generates magnetic field inside that second coil. Remember we talked about, right? Solenoid. So if you have something like that, if you have a current running through that, there's a magnetic field, right? Depending in which direction. You can think of like, let's say, then this second coil, is like basically nothing but a solenoid, right? And there's a magnetic field, probably like this, right? From that second coil. All right. So, and what happens here is you're moving it, closer to the first coil or moving it away from the first coil. That means, again, magnetic field generated by that, second coil, because now second coil has a current running through that. So second coil generates magnetic field. So then that magnetic field going through the first coil, and as the magnetic field through the first coil starts changing, because the second coil moving toward the first coil, now there is a current. What happens when a magnetic source, which is the second coil, moving away from the, let's say primary or first coil? Well, then there's again magnetic field, but in opposite direction. That means there's a reversal of the current, inside the first coil. That means, again, so this is, our first, sometimes I can call this primary coil, right? So that means this is the second coil or secondary coil. Again, our primary coil will get a current, induced current inside, right, in that primary coil, if the magnetic source is moving relative to the primary coil. Again, here we're using that. I have a lot of lines over there, but think like this. The idea here is this: the secondary coil, right? Secondary coil has a magnetic force, or magnetic field through the primary coil. Okay, and as it's moving toward, that magnetic field changes. So as the magnetic field increases, right, there is a current induced. As the magnetic field decreases, there is a current induced. But if magnetic field is constant, then the current in the primary coil will be zero. Okay, again, so when we move the second coil toward or away from the first, there's a current in the first coil, but only while one coil is moving relative to the other one. That means what I can do here is I can hold the secondary coil stationary and move the primary toward that secondary coil. I will get the same result. All right. Now, yet another experiment then was done by the Faraday, and that experiment was by taking the secondary coil and putting inside the primary coil and putting a switch, right, between the secondary coil and the power source. Again, this battery, right? So this battery is basically it's a power supply or power source. It's only connected to the secondary or second coil. Okay, only second coil. And one of the things we have here is if I close the switch, right? If I close the switch, then there's a current from the battery, right, that goes through the second coil. okay? But again, as soon as you have that, right, as soon as you have the second coil, current running through the second coil, it generates magnetic field. Okay, that means again, it generates magnetic field like this. Let's say inside that, a primary coil. But here's the thing, if I close the switch and there's a current, well, that current, here's what happens. When I close the switch, the instant, like let's say a millisecond or microsecond after I close the switch, there's an induced current in the primary coil, but then it goes to zero. Okay, that means, as soon as I close the switch, the current goes through the second coil, it generates magnetic field. Primary coil has an induced current, but after, like, let's say a second or so, it goes to zero. Now, why does it go to zero? Because what happens here is, remember, when the switch was open, let's say there is no current in the secondary coil. When the switch is open, there is no current at all. When I close the switch, okay, when I close the switch, then there's a current going through the secondary, right, secondary coil. But this current doesn't just go and basically increase from zero to its maximum instantaneously. It takes a little bit of time, maybe like, let's say, microsecond or a millisecond or something like that, right? But this current, as it's going through the secondary coil, remember, there was no current and no magnetic field, but now there's a current and now you start having magnetic field. But remember, that doesn't really happen instantaneously. It usually takes a little bit of time, microsecond or something like that, but that's a whole lot of time for the circuits. For us, it might seem instantaneous, but for the circuits, right, it's a quite enough time to be detecting some, let's say, induced current. But that means that instant when you close the switch, there's a current induced in the primary coil, because you go from no magnetic field to some magnetic field. Okay, but if you leave the switch on, right, or closed for a while, then that magnetic field through the a primary coil, magnetic field through the primary coil start becoming steady and constant. And if it's steady and constant, there is no induced current. Okay, now what we can do here is then we can open the switch. Well, when you open the switch, what happens here is that magnetic field that was there gonna disappear, but it doesn't just disappear instantaneously. It takes maybe like a fraction of a second or something like that, but that's enough time for the current to be induced in the in a primary coil. Let's say it's going to be in opposite direction, and then magnetic field goes to zero. As magnetic field goes to zero, then again there's no induced current. That means what happens here, there is an induced current only when you are, or the instant after you close the switch or you open the switch. Because when you're doing that, you're changing, right? See, when you just close the switch, you go from no magnetic field to a magnetic field. When you open the switch, the magnetic field that was already there due to the wire, right? Current running to the wire, now it basically disappears. Again, that means you are looking at, change in the magnetic field. Okay, so again, what we get is this: the induced current in the first coil, it is present only while the current in the second coil is changing. Again, when is it changing? When you just close the switch, it goes from no current to the maximum current. And during that short period of time, there is an induced current. After that, current becomes steady. So the induced current goes to zero. Remember, we have technically two currents, right? This current here is in the secondary coil, and I have induced current in the primary coil, okay? That means when you get this, right, when this starts increasing, when you just close the switch, you have this one also, starts increasing. But then as this becomes maximum, right, so as this becomes, as a function of time becomes maximum and steady, this guy then goes to zero, okay? And then after that, let's say you open the switch, the current goes in the secondary coil, right? Current goes from maximum to zero, but during this time interval when it goes from maximum to zero, again you get induced current, okay, in the opposite direction. But then as soon as you current in the secondary coil goes to zero, induced current also goes to zero. So that's why it only, this induced current is present only when the second, coil has a changing current, right? So that's why you can see the pattern, right? There has to be some kind of changing current, changing magnetic field, right, for the induced current to occur. That means the primary coil only has current running when something changes through that, primary coil. All right. Well, another example of the experiment that Faraday did was try to see, let's say, if you have the, this is the primary coil, right? So here's a primary coil, and there is no secondary coil at this point. So basically we have just your primary coil. Again, you can see, right, connected to a galvanometer. And then you have a device that generates magnetic field. Okay, so basically some kind of giant magnet that generates uniform magnetic field. So you can see B is constant. Okay, so B is constant. And the idea here is this. So remember, the idea was that if you have the magnetic field through the area of that loop changing, then there was a current induced. But if you have the magnetic field constant, okay, if you have magnetic field constant, and you can see right here what you have is magnetic field is constant everywhere. So if you move the, the coil up or down, you're not changing the magnetic field through that, coil. Okay, so if you move it a little bit up or a little bit down, you're not changing the magnetic field strength anywhere because it's same everywhere in this region. In this region, magnetic field strength everywhere the same. Okay, but what we can do here is we can still induce current. Okay, we can still induce current. Even though magnetic field is constant, okay, you can induce current by changing the shape or orientation of the primary coil relative to the magnetic field. That means one thing I can do here is this. So when the magnetic field is constant, the shape, location, and orientation of the coil do not change. If those things that doesn't happen, right? If those things don't happen, then no current is induced in the coil. Okay. That means if I leave the system like that, there will never be any current. So you're going to get zero current the whole time. You can wait 5 minutes, 10 minutes, 1 hour, nothing will happen. Okay. But here's the thing. Now, even if, let's say this is the one of the conditions with the magnetic field is constant, I can still induce current by changing the shape of the primary coil or changing its location or changing in orientation. That means you can do, a few other things by, to induce current. That means think like this. You take this coil and you move it from here to there, right? So kind of like you move it there, physically take it and move it there. What are you doing here? Well, you're moving from one region where there is a magnetic field through the coil to another region where there is no magnetic field through the coil. That means what you're doing, you're technically physically changing magnetic field through the coil by changing the location. Okay, so by changing location, that means moving the coil, outside of that region where there's a magnetic field, you are inducing current. That means while you're moving, there will be induced current. Okay, let's say while you're moving, you can have, for example, you can have it here. You can see right now half of it, there's a magnetic field. For the other half, there is no magnetic field. That means you are decreasing the magnetic field strength, right? As you move and move and move until there's absolutely no magnetic field. That means you have, decrease in magnetic field through the coil, there will be a current. When you take it from outside and move it inside, again, there will be induced current. Well, one thing you can do here is you can maybe take this coil and, change its shape by making it bigger. So let's say if you make it bigger like this, then you can see, right? So you have 1, 2, 3, 4, 5 magnetic fields going through the coil before. Now you have a whole lot more magnetic field going through the coil. That means you increase the magnetic field strength through the coil. There's an induced current. Okay, so changing the shape, which means its diameter. You change its diameter, you are increasing magnetic field. There's an induced current. You change location. That means you're changing amount of magnetic field lines going through the area through the coil, right? You're changing magnetic field. Well, the other option, we can do this, right? We can change orientation, which means, for example, you can see, right? It's oriented such that plane is perpendicular to the magnetic field. That means all the magnetic fields going through the plane. But one thing you can do here, you can change this by 90 degrees. So imagine you switching it by 90 degrees. That means now you have coil like this. Well, and this is the area of the coil. Well, in that case, let's say magnetic field here, we can see, right, is parallel to the area. When the magnetic field is parallel to the area, that means nothing going through the area. Well, in that case, again, you are changing the magnetic field, because you go from all the magnetic field through the area now to no magnetic field through the area. You're changing the strength of the magnetic field. You have an induced current. That means all of those things were discovered by Faraday by doing similar, or basically this experiments. Okay, so then the conclusion was this, right? So current is induced when any of those factors change. That means magnetic field, there has to be change in magnetic field. There has to be, let's say, change in area, right? Or, there has to be changing, like, let's say, orientation, which is, let's say, delta theta, okay? That means any of this, and in a way, when you're changing location, this goes into contribution for delta B, right? But when you change the magnetic field strength by either changing magnetic field value itself, or by moving the, changing the location of the coil of wire itself, right? You're changing magnetic field. You change the area, that means changing the shape. You're changing the magnetic field, right, strength, and again, you have induced current. Orientation change, again, gives you induced current. All right. Now, to better understand, let's say this last slide, in terms of, like, let's say, when the magnetic field going through the, center of the coil, we're gonna talk about this concept of magnetic flux. We kind of have seen this before from the electric flux. Remember, we talked about this as a Gauss's law. Remember when we talked about Gauss's law, we talked about electric flux, which was the electric fields through some kind of area A. Well, same thing here we have for the magnetic flux. Is that, let's say, here's your let's say this could be like an object that you have. What you do here is there's a magnetic field, right, through the object. Okay. Then what you do here is you take a small area of interest. You can write this delta A. That means your area of interest. And what you want to do here is look at how many field lines, or what is the amount of field lines going through that area A. And obviously, one of the things we can see here is the one that is parallel to the area doesn't do any contribution. But the one that are perpendicular to the area, right, then can actually contribute. And, because only the ones, right, those are the ones that are going through the area. Okay, those are the ones that are going through the area. Parallel component, the magnetic field doesn't. Even if you have, let's say, a magnetic field that has an angle phi, right, what you have here is you can look at the component of this magnetic field that is perpendicular to that area, because component of this magnetic field that is parallel to the area doesn't do any contribution. So again, this magnetic flux, and we're going to write this in terms of this capital phi, right, with the subscript B. This is magnetic flux. Okay, so the magnetic flux is proportional to the strength of the magnetic field, and it's proportional to the area A. Okay, and it's proportional then to cosine of angle phi. Okay, cosine of angle phi, which we're gonna consider, let's say, in terms of the component of the magnetic field there is perpendicular to the area of that, let's say, area of interest, right? Okay. Now, one thing we have here is, you can say, right, so let's say magnetic flux through the area is defined to be, here's the equation for that again. So magnetic flux equals magnetic field magnitude times area. And this is just basically, you can say, right, perpendicular component of the magnetic field. That means if magnetic field is perpendicular to the area, then it's just B times A. If magnetic field is not perpendicular to the area, then what you do, you take the perpendicular component, right? So perpendicular component will be B cosine of phi, and parallel component will be B sine of phi, okay? And this one, we don't really care at all because they don't do any contribution. We only look at the perpendicular to the area, component of the magnetic field, because you can see, right, this is the guy that's going through the area. This one is parallel to the area, so it's not going through the area. All right. So sometimes, for a student, it's kind of confusing to get that phi correctly. So then let me do this. Let me kind of describe this a little bit differently so you guys can maybe, visualize a little bit better. Okay. So here's what we have. So think like this. So those blue lines are the magnetic field lines, right? And then this is our area of interest. Okay, so this is our area of interest, right? That means this is our area. And then you can see, right? You have magnetic fields going through that area. Okay, so you can see, right? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9 magnetic field lines going through that area. Okay. Now what I can do here is, okay, so here's magnetic flux, and this is equals to B times A times cosine of phi. Okay, so B would be the strength of the magnetic field. Okay, so let's say, okay, so here's B is 10, Tesla, for example, right? And then, for example, area I'm given as, I don't know, let's say 5 meters square, for example, right? 5 meters square. Then when I'm writing this, so, let's say 10 Tesla times 5 meters square. Now the next is cosine of phi. Then what is the phi? What is cosine of phi? Okay, so to do that, let's do this. Let's define a vector A. Okay, so here's vector A, which has a magnitude same as the area of interest. So that's the A, right? Its magnitude is the area A, but its direction, okay, its direction is, I'm going to put this here n hat, and this is a unit vector, just like that I hat, j hat, k hat, right? N hat is a unit vector that tells you that this particular vector is a perpendicular vector to the area. That means you can see, right, this vector A is perpendicular to the surface, and it's always going to be perpendicular to the surface. That means vector A is always perpendicular to the surface. Again, right now, if I'm looking at this, I can say that B is 10 Tesla I hat, because it's pointing in a, let's say, x direction, right? Then vector A that I can say is A, area, right? And times n hat. N hat is a perpendicular to the, let's say, area vector. But since that particular vector A right now also pointing in the x direction, then I can also put it as A hat. That means n hat technically can be changed into I hat if the area is pointing in the x direction, for example, right? Now, one of the things we have here is, then when I come back here and I'm writing cosine of phi, so then what I do here is I take phi as the angle between B vector and A vector. That means magnetic field as a vector and area A as a vector. Well, you can see, right, my magnetic field is in the I hat direction. Well, my vector A is also in the I hat direction. That means both of them are horizontal, both of them pointing in a horizontal direction. That means angle between them is 0 degrees. Okay, that means I come back here and put 10 Tesla times 5 meters per square times cosine of 0 degrees. And what I get here is I get 50, right? 50, then Tesla times meter square. Okay, that means that's my magnetic flux. Okay. So what happens then when you change the orientation of the area? Well, when you change the orientation of the area, so one of the things you can see here is this. So magnetic field still, let's say, was same, let's say 10 Tesla, okay, in the I hat direction, right? It's still pointing in the x direction. But my vector A, if you're changing the area orientation, right? Well, my vector A changes with the surface because it's always perpendicular to the surface. Now then what I get here is, so let's say vector A still has a magnitude of let's say 5 meters square, right? Its magnitude doesn't change because area that doesn't change. But what happens here, now it has a direction, let's call this phi here, right? So there's a direction, there is no longer I hat, right? So it's a little more complicated, but all I have to do here is find this, phi for that, area relative to, let's say, positive x-axis. Then let's say this is, I can say that now area here is, or that vector is, let's say, I don't know, 30 degrees, right? With respect to the x-axis. Okay, remember, x-axis is always a reference position, right? So then I can just use it like that. Then when I'm calculating a magnetic flux, what I will do here is I will say, okay, it's, magnetic field strength, the magnitude, area magnitude, then times cosine of phi, which is angle between magnetic field and then area vector. And this will be 10 Tesla times 5 meters square, then times cosine of, you can see, right, phi here is the angle between magnetic field as a vector and area as a vector. And that's, let's say, 30 degrees, okay? So that means, one thing you can have here is, you can say then cosine of 30 is 0.866 times 10 times 5. Then magnetic flux here is 43 Tesla meter square. That means you are decreasing magnetic flux. If you change the orientation, right? So you can see, right, when the phi was 0, we had 50. When phi here is increasing, right? That means, let's say, when the phi here is between, greater than 0, but let's say less than 90, the magnetic flux is decreasing as you increase the, the flux, or increase the, this phi. All right, so what happens when you increase the phi, that means increase the surface all the way so that surface is parallel to the magnetic field. That means the surface itself, right? Your surface is parallel to the magnetic field, but then you can see, right, vector area A here is perpendicular to the magnetic field, okay? That means when I'm calculating magnetic flux, it's equals to then, same 10 Tesla for the magnetic field, 5 meters square for the area, then cosine of phi between area vector and magnetic field vector. And you can see, right, they are perpendicular to one another, so cosine of 90 degrees. Then the flux, magnetic flux in this case, is 0. Now, what does it mean physically speaking when the flux is 0? It means no fields going through the area. And you can see, right, all those fields are parallel to the area. Nothing is going through, nothing penetrating the area. That means the flux here is 0. All right, so that's kind of what we have. So this is, this is the idea, right? This is this concept of magnetic flux, which is, again, represents just the number of field lines going through some area A. And area A is our area of interest. So how much, flux just represents basically how many field lines going through that area. Flux is 0, means no field lines going through that area. Flux is, maximum, that means maximum amount of field lines going through that area. All right, so then one of the things we have here is then Faraday, when he wrote down his law for the induction, for the induced current and induced EMF, he did that in terms of flux, okay, in terms of flux. Because one of the things we have is this. So here's the equation for the flux. So it's magnetic field strength times area times cosine of phi, which is the orientation between magnetic field and area. And remember, if we go back and look at the, the induced current, so remember that we had a, let's say, a coil of interest, right? That had, area A, and there was, like, let's say, then magnetic field, right? Through that, area A of interest, or through the coil. So let's say there was a magnetic field like this. And we can see this. I can calculate a magnetic flux for this particular case, right? I can say, all right, so this is my magnetic field. So I can find the magnetic flux by taking this magnetic field. Let's say, again, let's say this was 10 Tesla, and area, which was 5 meters square. And let's say here's that area vector, right? Okay. So in this case, I can calculate this to be, let's say, same thing, right? So let's say 10 Tesla times 5 meters square. And here you can see, right? Hopefully, if I'm asking you right now, what is the, the phi, right? For the flux equation. if you a little bit think about it, you should be able to see that this is 0 degrees. Again, because magnetic field and area vector, right? They are parallel to one another. So then angle between those two are 0 degrees. That means what I get here is I get 50 Tesla times meter square as the magnetic flux. All right, but here's what we're gonna do. We're gonna take this Tesla times meter square as a unit, and we're gonna define that as Weber. That means units of magnetic flux is not gonna be Tesla times meter square, which is, it is technically, but we're gonna define that to be Weber. That means I can say that magnetic flux is 50 Weber. All right, now here's then what I have. Imagine that if I change the magnetic field from 10 to 20, that let's say in 5 seconds, I change it from 10 to 20. So then this is my, initial magnetic flux. And if I calculate my final, when it goes from, magnetic field goes from 10 Tesla to 20 Tesla, you can see, right? If I plug in that, I'm gonna get 100 Weber as my magnetic flux. You can see, right? I changed my magnetic flux. Why did I change my magnetic flux? Because I changed the magnetic field strength. Okay, so remember, this is consistent, right? That means, what we have a change in, change in magnetic field. Well, magnetic field changes magnetic flux. What if I change the area of this coil? Well, see, if I change the area, that means I'm changing this. So imagine I go from 5 to 10 meters square. That means, again, my magnetic flux will increase, right? Because magnetic flux directly proportional to the magnetic field, area, and then orientation. Just like some of those things we talked about for the induced current, right? Induced current will happen if you change magnetic field strength, if you change the shape, which is the area, or you change the orientation, which is cosine of phi. That means to understand this EMF, right? This induced current and induced EMF, changes that. That means flux would change if you change magnetic field strength, if you change the shape, and if you change the orientation. So then what he said is this induced EMF will occur if there is a change in flux as a function of time. Because when you're doing, let's say this induced EMF, right? When you're talking about changing flux as a function of time, you're assuming that this change doesn't happen instantaneously, but happens over, a short period of time. Okay, so again, milliseconds, microseconds, but remember, I told you, right? So let's say if you're moving the magnet toward the primary coil, the magnetic field changes with time, right? It doesn't just go instantaneously higher value. It's like as you're moving closer, its value slowly increases. As you close the switch, the value of the current, slowly increases to its maximum and things like that. So that means what I have here is, so this technically what we get here is this. When you change in magnetic flux as a function of time, you technically has the ability to change either the magnetic field strength, or you change basically the area, right? Or you change the cosine of phi. And all that is as a function of time. That means, and we put the absolute value, that means, you can have increase or decrease. We're just looking at the, the magnitude or just the positive value of the EMF. And remember, this is EMF, so it has units of volts, okay? That means one of the things we're gonna do here is we're gonna say that if the flux through that coil area changing, there's gonna be induced EMF. Well, if there's induced EMF, there's gonna be an induced current. That means you generate electricity, but to generate electricity, you have to change the magnetic flux, okay? Okay, all right, so let's look at this example over here. All right. So in a physics laboratory experiment, a coil with 200 turns enclosing an area of 12 centimeters square is rotated in 0.040 second from a position where its plane is perpendicular to the Earth's magnetic field to a position where its plane is parallel to the magnetic field. All right. So the Earth's magnetic field at the lab location is 6 × 10⁻⁵ Tesla. For part A, what is the total magnetic flux through the coil before it is rotated, and what is after it is rotated? For part B, then what is the average EMF induced in the coil? All right, so let's see then what we have. So we're given, there's our coil is not just a single coil, but 200 turns. That means we're given N is 200 turns, right? So N is 200. And one of the things we're going to see here is that technically that equation. So if I kind of go back to this equation, you can say that there's also an N here, part of your equation. So it's N times. So let's say if I come back to this equation, you can say there's like, also N over there, which is N number of turns. So N number of turns times change in flux through the coil. All right. That means N is 200. So we have the area is 12 centimeters. That means, which is 12 centimeters square. Okay. And we're going to have to change that. We're going to have to change that because we need meters square. So what we do, we take that, 100 centimeters is 1 meter, but you have to square this as well so that, centimeter square and centimeter square cancels out. And what we're going to get here is 12 times 10 to the negative 4 meters square. Okay. And we're given that delta T here is 0.04 seconds. Okay, again, N is 200. Okay. And we're given that magnetic field strength is 6 times 10 to the negative 5 Tesla. Okay. Now, what we have here is this. We start, okay, so we start with, you can see, right, a plane of that coil is perpendicular to the Earth's magnetic field. Okay, that means, for example, imagine if this is the Earth's magnetic field. Okay, that means this coil here is like this, where you can see, right, the plane itself is perpendicular to the magnetic field. That means if I want to find the flux at that instant, it will be magnetic field times the area, then times cosine of phi. Okay, now the question is, what is phi in this particular case? All right, so let's see what we have. Well, if you said 90 degrees, you're wrong. Okay, but for example, if you said 0 degrees, then you're correct. Because remember, what we do here is we take the surface and we use this vector A, which is perpendicular to the surface, right? And what we do here is, you can see, right, this vector A and the magnetic field, they are parallel. And remember, the phi here is between them. So phi here is 0 degrees. So then if I'm calculating a magnetic flux here, it will be in terms of magnetic field, which is, well, let me do it here so I have more room. So magnetic flux is magnetic field area, then cosine of phi. So there will be 6 times 10 to the negative 5 Tesla, then times 12 times 10 to the negative 4 meters square, and times cosine of 0 degrees. So then I can calculate the flux. Oh, sorry. So then the flux will be 7.2 times 10 to the negative 8 Weber. All right. Then what we do here is we change the orientation so that it says the plane is parallel to the field. What does that mean? Well, let me use different colors so we can see that. So think like this. This is, what happens afterwards. So you take it and you kind of rotate it by 90 degrees. So let's say now this is how the coil will look like. Okay. And this is its area. Well, what is then the vector A in this case? Well, vector A will be pointing out of the page. Okay. That means this is going to be my then initial phi, and this is going to be my final phi. What is final phi here is 90 degrees because vector A is pointing out of the page, magnetic field is upward, and they're perpendicular. That means if I'm calculating, you can say, right, this is an initial, and if I'm calculating the final magnetic flux, this will be BA cosine of 90 degrees. Well, I'm going to get 0, which is the due to the fact that cosine of 90, right, gives you 0. That means if you rotate the, this coil, right, to be where the plane is parallel to the field. Well, plane parallel to the field means no field lines going through that plane, which means that phi is 90 degrees because you are taking the angle between magnetic field and vector A, which in this case out of the page. All right. So what we get here is then you can see, right, that means you go from 7.2 times 10 to the negative 8 Weber at that, t equals 0 time to 0 Weber at t equals 0.04 second. That means in 40 millisecond, right, you change the flux to 0. All right. Now what we get here is then induced EMF is equal to an n times change in flux over time. And generally what we get, this equation is usually for the average, right? So this is for the average EMF, because every time you're doing delta something over delta t, you're calculating the average. Okay. So, but remember, if let's say, if you assume that EMF stays constant, right? So it's the same as, always, but, it's generally better to, consider the average itself, right? So that means here you're calculating average EMF. So then this will be 200 turns, then times, remember, change in flux is final minus initial, divided by delta t, which will be 200, then finally 0, initial 7.2 times 10 to the negative 8 Weber, divided by 0.04 seconds, right? And what we're going to get here is for the EMF, we're going to get 0.36 millivolts. Okay, so it's going to be 10 to the negative 4 volts, right? So we write it as 0.36 millivolts. All right, so it's not a lot, but still, by just changing that, you take it, 200 turn coil and just rotate it 90 degree, you generate EMF. That means that's 0.36 millivolt. And, there's going to be current depending on how much resistance you have in your wires. That means you can calculate then induced current from that. All right, so here's then what we get. The next is we're going to talk about Lenz's law, all right? And Lenz basically considered basically why there is an induced current. So it's kind of like more conceptual question where Faraday was able to calculate, okay, and discover that, let's say, okay, so every time you change magnetic field, orientation or shape, all those things, right, there's induced magnetic field. So Lenz was able to kind of, in a little bit different way, describe the same, let's say, the same experiment. In a way, let's say, why do we get that increased current in the first place? All right, so, and there's no mathematics here, basically, it's just all conceptual. So you can conceptually explain why there is a, induced EMF and induced magnetic field, okay? So let's talk about that. Okay, so what we get here is this. So let's say you have this coil, right? So coil, this is again, it's a coil that has absolutely no connection to anything. That means this is just a conducting coil, all right? So circular conducting coil, and it's not connected to anything. Okay, so, and this is, let's say, the area of interest through the, through the center of the coil. But what we get here is this. So there is a magnetic field through that coil. So let's say this is our original magnetic field. So this is the magnetic field at t equals 0. Okay, that's the magnetic field at t equals 0. Okay, that means one of the things I can do here is I can calculate the flux because there is here's the vector A. I can calculate the flux, magnetic flux, by taking magnetic field times the area times cosine of phi. Now the question is there a magnetic flux here? Yes, there is a magnetic flux. Why is there a magnetic flux? Because I have magnetic field, I have a coil with some area A, and I have orientation such that B and A, right, basically give me let's say 90 degree phi. That means angle between them is not 90 degrees. So BA cosine of phi is some kind of value. So for example, I will calculate, I don't know, 20 Weber, for example, just shooting a number. So let's say if I calculate that, this is what I get. All right. So also what we can say is that it's a positive, positive flux. Why is it positive flux? Because, a phi here is, between 0 and 90. Okay, between 0 and 90. So you're going to get a positive flux. All right, so then let's see what happens. If you don't change magnetic field, if you don't change the orientation or shape of the coil, your flux will remain constant. That means this is t equals 0. This is some later time t prime, right? And what I have here is, if you're not changing any of those things, right, then this fb prime is same as, before. That means flux is the same as before. That means if I don't change any of those things, that means magnetic field is not changed, area is not changed, orientation is not changed, my flux is not changing. And when I'm looking at this EMF, it will be n times, change in flux over time. And since if I'm not changing any of those things, I'm going to get no EMF. Well, no EMF, no induced current. Okay. But what if I start changing something? And what we're going to do here is we're going to change magnetic field strength. So imagine now, as a function of time, what we're going to do here is we're going to increase magnetic field. That means we're going to increase by this much. Okay, we're going to increase by that much. And what we're going to do here is we're going to change it by that much every second. That means there's this change in magnetic field. For example, if I do 5 Tesla, which means that every second magnetic field is, increasing by that much. That means, if my magnetic field was, let's say, to start with like 10 Tesla, 1 second later it's going to be 15. Then it's going to be 20, 25, 30, 35. That means every second is going to, increase by, let's say, this much. See, my change in magnetic field is 5 Tesla. That means every second is going to increase by that much. So if it's a delta B, delta T is positive, that means it's going to increase by that much. If, for example, delta B, delta T was negative, right? Then it will then decrease by that much, right? So, but let's say right now we have an increase in magnetic field. That means every second magnetic field is increasing. That means, for example, now I don't have that, right? I don't have this. My magnetic flux a little bit later will be, larger. Why? Because this guy, see, if I'm doing magnetic flux as a prime, right, become B prime A times cosine of phi. Well, A doesn't change, cosine of phi doesn't change, but B is changing. B prime is bigger than B because 1 second later my B is, 15. Before it was 10. That means it's increasing. Well, that means this will be true. My magnetic flux will be, greater as a function of time. It's going to become more positive and more positive. It's going to increase. Okay. Now, when I come back to this equation, I can see that, well, I have change in magnetic flux. That means this term here is no longer 0. Okay. That means EMF is going to be then, EMF is going to be non-zero. I'm not going to get 0 anymore because I have non-zero flux. And it's going to happen during some time interval t, right? And n can be either 1 or anything you want, right? So if it's just 1 coil, then n is 1. But the idea here is this. If you start, increasing your magnetic, let's say magnetic field, then magnetic, flux going to be changing, which then will induce EMF. Okay, there's going to be then induced EMF. According to the Faraday's law, I can use that to calculate. Okay, I can use that to calculate. Okay, now here it says induced EMF is negative. Well, the reason it is negative because the general equation for EMF technically has a negative. So it's negative n times, let's say if I'm not using the absolute value, right? So delta phi delta t. Okay. But most of the time in this class, we don't really worry about that. In higher classes, we do that. But right now, we always just take absolute value always, everywhere. So we just, let's say, use that to find how much EMF it is. But the idea here is this. as soon as I increase magnetic field, right? As soon as I increase magnetic field, then I get magnetic, magnetic flux changing. And what it does, it then gives me induced EMF. Okay. Now, induced EMF here in this direction means that also gives you the direction of the current through that coil. That means there's going to be a coil in this direction inside. Okay, that means clockwise, let's say. Okay, so there is a clockwise, current in that wire, in that loop. Okay, so here's then what we get. So Lenz tries to explain why is there a current in that particular direction through that, through that loop. Okay, so let's say why is the current is not in opposite direction? Why it has to be, let's say, clockwise? Why is it not counterclockwise? Well, think like this. The idea here is this. There is a current in that loop because the system does not like the change that you have introduced. That means the magnetic field of 10 Tesla initially that you had through the loop, and let's say this magnetic flux of 20 Weber that you calculated, it got used to that. So let's say that was the equilibrium, a condition for that. That means if you have 20 Weber, right, which is magnetic flux, it was happy with that. But now when you increase magnetic field, let's say you made this 30 Weber, which you increased it because you increased the magnetic field. And the system doesn't like that. So the system gonna try to, remember one of those, restoring, properties, is gonna try to restore system back to what it was before. That means you increasing the flux, well, it's gonna try to then decrease the flux so that flux becomes, 20 Weber, same as before. How can it do that? Well, it cannot change this magnetic field. It cannot change this, increasing that, there's nothing you can do about that. That's some kind of external source, okay? But here's what loop can do. Loop can generate its own magnetic field. So for example, imagine if the loop generates magnetic field in the opposite direction, where the magnetic field as a function of time is -5 Tesla, then this positive 5 Tesla external magnetic field increase can be canceled by -5 Tesla, let's say magnetic field in the opposite direction, introduced by the loop, right? So technically, if the loop pumps magnetic field in the opposite direction of the original magnetic field by the same amount, then it can cancel the effect, right? Okay, so you're increasing by 5 Tesla. I'm going to decrease it by 5 Tesla and push it back to the equilibrium that it was before. Okay, so then how can the loop generate magnetic field opposite of that? Means let's say in this case a downward magnetic field. How can it then generate downward magnetic field? Well, the loop can do that if there is a current in the loop, right? Remember we talked about in chapter 20. Remember that right-hand rule, the second right-hand rule, which is magnetic field current combination. Use your fingers right now, use your right hand, where your fingers give you the direction of the current needed to have your thumb pointing down. Think like this. If your thumb is pointing down, you can see, right, your fingers have to curl clockwise. That means if the loop generates clockwise current, it can generate downward magnetic field. So this is known as induced magnetic field. It can induce its own magnetic field. And it has to be in the opposite direction, right, to cancel the increase. And that's why the current has to be clockwise, because the magnetic field that loop has to generate to basically fight the change or increase in magnetic field has to be in opposite direction. And that means downward. That means the current in the wire in this loop, right, has to be clockwise. And Lenz basically tells you this. It tells you that loop generates induced EMF and induced current so that it can fight the change in the magnetic flux. That means that's why there's always only induced EMF and induced current if you're changing the flux. If you're not changing the flux, there's nothing to restore. Everything is in equilibrium. But as soon as you do that, it has to react, right? And it tries to, fight the increase by trying to decrease the magnetic field, which it can do by pumping magnetic field in opposite direction. All right. Same way you can think of, like, let's say, same scenario, right? But what you get here is, here's your original magnetic field. Let's say it's, same as before, 10 Tesla, right? So let's say you have 10 Tesla magnetic field, and you have, let's say, that flux of 20 Weber, with respect to this original, magnetic field. But this time we're going to be decreasing magnetic field. That means what I have here is that change in magnetic field over time is going to be negative 5 Tesla. That means, or let's say negative, I don't know, let's say negative 2 Tesla, right? That means every second is going to be increased by 2. That's going to be 10, 8, 6, 4, 5, 2. And so that means magnetic field is decreasing. Well, if the magnetic field is decreasing, that means magnetic flux as a function of time will also decrease. Okay. Well, again, you are changing the flux. Again, the system doesn't like that. And loop gonna try to fight that change in magnetic flux. Well, what can it do? It can do only one thing. It can try to restore the equilibrium by either, pumping more magnetic field, right? Either in the, in the previous case, we looked at, when the magnetic field is increasing, while the loop can pump more magnetic field in the opposite direction to, fight that change. Okay, but now what you're doing, you're decreasing the magnetic field. Well, that means, your flux is positive still, because, you can see that phi here is between 0 and 90. Okay, so, but it becomes less positive because you are decreasing the flux. Okay, you are decreasing the flux. Now, what can then magnetic, what can then the loop do? Well, change in magnetic field is negative. One thing it can do, the loop, right? Loop can then maybe pump more magnetic field, right? In the same direction as it was before. You can see, right? If the loop generates magnetic field in the same direction, and the magnetic field that it generates, let's say it's plus 2 Tesla, that means every second it pumps 2 Tesla magnetic field. Well, won't this, cancel that effect? Well, it should, right? It tried to then restore the equilibrium. And that's what it's going to do. It's going to then try to pump magnetic field in the direction of the original magnetic field. That means upward, right? Out from the area. Well, if it has to pump magnetic field upward, then it can only happen, you can see, right? If your thumb is pointing in the direction of the original magnetic field, right? That means your fingers have to curl counterclockwise. So that's why EMF and then the current in your circuit is counterclockwise, because only counterclockwise induced current produces upward magnetic field, and only upward magnetic field, since it's in the same direction as original magnetic field, can restore the balance because the magnetic field is decreasing. All right, so hopefully you can wrap your head around this. So try to maybe watch this again a few times, but the idea here is it's a conceptual way of looking at why the direction of the current is the way it is. Again, in this case, it has to be counterclockwise because it needs magnetic field upward in the direction of the original magnetic field. All right, and obviously you can have other scenarios too. So for example, here, so this is our area of interest. So this is our area vector, right, upward. But what we get here is the magnetic field here, as you can see, right? So this is the original magnetic field is downward. That means kind of goes down, basically through the area. So it's a downward magnetic field. Okay, so this downward magnetic field, then again, as a function of times, starts increasing. That means you can see, right, magnetic field is increasing. Okay, that means, for example, now magnetic field as a function of time is plus 5 Tesla. Again, plus means that whatever the direction you have for the magnetic field, it starts increasing. So that's why it's plus. It means it's increasing, which means the change is in the same direction. Well, in this case, if I calculate my flux, I'm going to get a negative value because you can see, right, phi here is, greater than 90, but less than 180. Okay, so that's why flux is negative. So one of the things that we can do here is this, okay? So magnetic field is increasing. Okay, it's increasing downward. Well, again, the loop doesn't like that, and the loop gonna try to fight it. How can the loop fight it? Well, the loop can fight by restoring it back to its original value. So the way it can do that, then to pump magnetic field in the opposite direction, right? Because if this is by how much it's increasing, well, if you pump just as much but in the opposite direction, those two can cancel each other. That means right now, induced magnetic field, right? So B induced has to be upward because change in magnetic field is downward. Well, what gives you upward magnetic field, induced magnetic field? Well, it has to be, because this is the direction of B induced. That means your fingers has to be, curling in a counterclockwise direction. That means if you have a counterclockwise induced current, if your current goes counterclockwise like this, then there will be a magnetic field generated by the loop, in the opposite direction of, and it will try to cancel magnetic field. Again, Lenz's law allows you to find the direction of the induced magnetic field due to that induced current, right? That means the current has to be counterclockwise in this case. All right, so the last case that we're going to see here is kind of like the reverse of that. That means the magnetic field is down, but now it's decreasing. So that means now, think like this, it's decreasing. That means technically this is the change in magnetic field as a function of time. Because what you get here is, let's say you originally had, 10 Tesla, but now as a function of time, it decreases by 2 Tesla every second. That means that's why it's -2. That means every second, you can see, right? So this is then change in magnetic field. That means it decreases every second. You can like change it. So let's say right this, right? So what can the loop do? Well, since you're decreasing the magnetic field, the loop can try to increase by the magnetic field by pumping more magnetic field in the same direction. That means the induced magnetic field has to be downward, right? Has to be downward, okay? That means it has to be downward, and so this is B induced, okay? So that means right now, what you need to do here is, so technically this just tells you that you have to use a right-hand rule, right? But you have to understand right now, your thumb will be pointing down because that's the direction of that, the direction of induced magnetic field. And then your fingers, right, will be then curling, clockwise, right? It has to be curling clockwise to give you downward magnetic field. So that's why the current here and EMF, right, both of them are clockwise, because only clockwise, and again, so you can see, right, EMF is negative, means it's just clockwise, because remember the clockwise was negative, right? That means EMF and current, they have to be clockwise in order for you to get downward induced magnetic field, which will then, try to cancel this decrease. Okay, try to cancel or fight that decrease in magnetic field. All right, so let's summarize all this. So Lenz's law is a convenient method for determining the direction of an induced current or the EMF. And the direction of any magnetic induction effect is such as to oppose the cause of the effect. So that's the key. It's oppose the cause of the effect. Okay. So here's the figure, right? So it says you have a coil, and so this is the external magnetic field. So this is the external magnetic field. That means, upward. But it's changing. And it's changing in the same direction, means that it's increasing. So you can say, right, B, you can say B external, right? So B external is increasing. B external increasing. Well, remember, you probably already figured out the pattern. If B is increasing, induced B then has to be in opposite direction. Well, if B is decreasing, then induced B has to be in the same direction as the external magnetic field. But in this case, because B external is increasing, B induced has to be in the opposite direction, right? It has to be in the opposite direction. Well, in order for the current to generate downward magnetic field, the current has to be clockwise, right? So that's why you have a clockwise current, so it can generate this downward induced magnetic field. So the magnitude of field is increasing, so there's an induced EMF driving a current clockwise, so that magnetic field induced will try to fight, right, that effect, fight that change. So it's going to try to oppose that change. All right, so then you can understand why whenever you were moving magnet upward or downward relative to the primary coil. That was the very first experiment that we looked at from Faraday, right? So when you're moving the magnet toward the coil, primary coil, or away from the primary coil, then what you get here is you get different direction for the current. So this kind of like doesn't really show that, because this shows like, okay, here's north moving. Well, if the north is moving, well, magnetic field strength starts increasing, right? Well, if that starts increasing, then loop generates magnetic field in an opposite direction. So that means it has to give you counterclockwise current. So the next slides, so for example, right now, just ignore on the right side. So the next slide tells you, okay, so how about if the magnet where the north is facing the loop is moving away? Well, when it's moving away, then magnetic field that it has through the loop, it starts decreasing. So when it's decreasing, right? So this is decreasing. That means the magnetic field induced has to be in the same direction as external magnetic field to reinforce it, right? So that's why it has to then give you, clockwise current. So you can see, right? Clockwise current when the magnetic field is decreasing, or counterclockwise current when magnetic field is increasing through the loop. So that's why you have two different directions of the current. Now you can see that same thing is here if the south was facing, right? Kind of same idea, but the magnetic field direction, external magnetic field direction is just different, right? But you can see, right, moving away compared to moving toward, you get the two different, direction, current induced, clockwise versus counterclockwise. All right, so then let's look at this example over here. So you have a circular loop of wire is in a region of spatially uniform magnetic field. The magnetic field is directed into the plane of the figure. Determine the direction, clockwise or counterclockwise, of the induced current in the loop when magnetic field is increasing in its magnitude, or if the magnetic field is decreasing in its magnitude, and for part C, if the magnetic field constant value. Okay, so some B naught constant value. All right, so let's look at, for A. Well, A tells you this. So the magnetic field into the page, so magnetic field, so let's say this is external magnetic field, right? So let's do this. So external magnetic field here is into the page. So this is into the page, right? Well, what it means here is then if it's into the page and it starts increasing, okay, it starts increasing like this. Let's say start increasing. Well, in which direction will be then current? Remember, the current in this, circular loop will be, only in order to pump magnetic field, induced magnetic field to, fight this change in external magnetic field. That means if the magnetic field into the page is increasing, the loop gonna try to pump magnetic field in the opposite direction to try to, decrease it, right? That means the magnetic field induced, has to be in opposite direction. So that means it has to be out of the page, okay? Because see, this is the key. If the external magnetic field is increasing, induced magnetic field has to be in opposite direction. Well, what current gives us magnetic field induced out of the page? Well, you have your thumb out of the page, and you can see, right, if you curl your fingers, it will then give you current to be counterclockwise. Okay, so you have a counterclockwise current in order to get out of the page, a magnetic field, induced magnetic field. Okay. Otherwise, what you get here is, you know, if the magnetic field induced is into the page, your external magnetic field is increasing even more. So the idea here is that it has to fight the change. It has to oppose the change. All right. So let's look at B. So for the B, what we get is this. External magnetic field is still into the page, right? But this time it's decreasing. Decreasing. That means becoming less and less. Well, again, loop doesn't like that. So it wants to, you know, change. It wants to oppose this. Well, to oppose that, the induced magnetic field has to be in such that it increases the external magnetic field. That means it has to be in the same direction as the original magnetic field. That means it has to be into the page. All right, so what direction current gives us into the page magnetic field? Well, use your right hand. Your thumb, which is B induced, is in the direction of the original magnetic field, which is into the page. And you can see, right, you have to curl your fingers for the direction of the current. And in this case, like induced, right, I induced will be clockwise because, you know, thumb into the page gives you clockwise current. All right, for C, what happens if the B external is into the page, but constant, some constant value B naught? Well, if it's constant, doesn't change, what is then B induced? Well, it's zero. Why is it zero? Because there's nothing to restore. Your value doesn't change as a function of time. Remember, this is not fighting the magnetic field that is there. It's fighting the change in that magnetic field. But if nothing is changing, well, there is no induced magnetic field needed for that. Then what is induced current? Well, also zero, because you have to have, in order for you to not have a magnetic field, you need to have no current, because any current in your loop going to give you a magnetic field, and then you're going to start changing things. But the loop doesn't change, right? It only reacts to change. So the current here in this case is zero. All right, guys, so let's continue here. Here's one more example. You have two closed loops, A and C, are close to a long wire carrying a current I. That means what we have here is we have a long wire with a current running through that. And you have two loops, C and A, which are, close to this wire, but they have no current, okay? So they're not connected to anything. You can think of like this guy here is some point connected to some, power source. So find the direction, clockwise or counterclockwise. So it's basically, we're going to be using the Lenz's law here, of the current induced in each loop if I is steadily decreasing. All right. So, and while I is decreasing, what is the direction of the net force that the wire exerts on each loop? Okay. Explain how you obtain your answer. All right. So here's then what we get. So let's say you have a wire with the current running through that. So let's assume that for a t equals 0, right? So you're looking at t equals 0, and let's say the current here is, I don't know, 10 amps. Well, remember, if you have a wire that has a current running through that, well, this wire generates magnetic field all around it. And if you use the right-hand rule, your thumb is in the direction of the current, you can see that everywhere above it, the magnetic field will be out of the page. That means this is the magnetic field generated by that wire. So magnetic field everywhere out of the page. That means through the loop C, magnetic field generated, this external magnetic field generated from this wire will be out of the page. But everywhere below the wire, magnetic field is into the page. Right, magnetic field into, so this is, you can think of this is B external, right, due to the wire. Okay, so here is, out into the page, here is out of the page, but still same magnetic field generated by the wire. That means for the loop C and A, that's the external magnetic field generated by the wire. Okay, so if the current is constant, if the current is constant, there will be no induced current in loops C and A. That means, yes, there is a flux through that, loops C and A, but if you're not changing the flux, if you're not changing the current, you're not changing the magnetic field, which means you're not changing the flux. So that if now flux changing, no induced current. But for now, let's say we start changing the current by steadily decreasing it. Well, remember, this is a straight wire. Magnetic field at any point, so let's say this point P. If I do that, I can look at, okay, so it has a distance R, I don't know, let's say RC, right? So from this wire, and I can calculate magnetic field at that point, which will be mu naught times the current divided by 2 pi times RC. And I can also calculate the magnetic field over here, right? At that particular magnetic field. Let's say point P prime. Then this will be R, A, since it's a, wire at the loop A, right? So where's the magnetic field there? Well, it's mu naught times the current divided by 2 pi times RA. Remember this equation, right? This is the equation that we can use to calculate the magnetic field any distance from the straight wire. Well, as you can see, right, as long as the current is constant, the magnetic field is the same. But if you can see, right, magnetic field is proportional to the current. This equation tells you that. You decrease the current, you're decreasing the magnetic field. That means as we are decreasing the current here, right, the magnetic field through the loop C and through the loop A is also starts decreasing, okay? That means things like this. So what you get here is this. So I'm gonna use this as BC. So BC is the external magnetic field through the loop C. So BC external, okay? So now it is out of the page, and it's decreasing. So it decreases. Well, what would then loop C do? So remember, so the loop C has a magnetic field out of the page and it is decreasing. Well, remember, it's going to try to, fight that decrease. So it's going to try to fight, it's oppose that decrease. How can it oppose the decrease? Well, it can try to generate its own magnetic field, try to reinforce it, right? Well, that means in order for it to reinforce the original magnetic field, it has to pump magnetic field in the same direction as the original magnetic field. That means BC induced should be also out of the page. Okay, should be also out of the page. Okay, again, why should it be out of the page? Because the idea here is, since the out of the page magnetic field is decreasing, the loop can generate its own magnetic field also out of the page and push it back to its original value. So what current gives us out of the page induced magnetic field? Again, your thumb is out of the page. You can see then the current in that loop C has to be counterclockwise. So this is current C. So it has to be counterclockwise. All right. Now let's look at then loop A. So for the loop A magnetic field, so this is loop A, so BA external is then into the page. Okay, and it is decreasing, so going down. Well, then A will be inducing, right? Loop A will be inducing its own magnetic field, again, in the same direction, because you have to reinforce it, right? You have to pump magnetic field in the same direction. That means also be into the page. Right, so it has to be into the page as well. That means the magnetic field that it induces will also be into the page. What current will give you into the page, be induced? Well, again, your thumb is in the direction into the page, then you curl your fingers, and you can see, right, it has to be clockwise current. So current A will be clockwise. All right, that means we got counterclockwise current in loop C and a clockwise current in loop A. Okay, then that's part A. How about part B? Because one thing we get here is this. Then I have wire has a current, loop C has a current, loop A has a current, and any conductors with current nearby, they exert force on one another. So then let's look at in terms of what will be the force on the, on loop C due to the wire. Well, this comes from the fact that we learned in the last chapter that, remember, if you have two wires with the same direction current, they attract each other. Okay. And one of the things I have here is this. You can see that the current in the loop C has four directions, sort of like, let's say, right? So those parts don't contribute at all, okay? Because over there, the current is perpendicular to the, wire current. But over here, so you get one current over here to the, opposite direction, and this one in the same direction. That means there's a liberal force here pushing because, you can see, right, to the right and to the left. So, this basically the top part of the loop C is going to be, pushed upward. But then the bottom part of the loop C can be pushed toward. But because the bottom part is much closer overall, what you're going to get here is overall there's going to be force toward this wire. So there's going to be force on wire. So let's say force on C, okay, is going to be toward the wire. Okay. Well, how about the loop A? Well, loop A also, see, let's say if I look at this portion, see there's a current to the right, just like the current in the wire. That means this part is going to be pulled toward the wire, but this portion has the opposite direction, is going to be then pushed. But this part that is closer and is going to be pulled, right, it's much stronger, much closer, so it's going to be much stronger. Then overall, there's going to be, attractive force on this, loop A. That means both loop A and loop C are overall going to be pulled toward the wire. So it's going to be attractive force from the wire. All right. So now we're kind of moving to a what we call motional EMF or motional electromotive force. So remember, electromotive force was what we call EMF, was basically some kind of voltage source, okay? And one of the things we learned here is if you have a battery, negative, positive terminals, right, connected to some kind of load, right, so capacitor or a resistor, whatever it is, right, so it's going to give us a current going through that, circuit, right, and, this battery acts like a driving force, right, that's what drives those charges, okay, so that's why we call this EMF, something that can, so EMF or like that, right, something that can basically do the pushing inside the battery. Remember, the charge is being pushed from negative terminal to positive terminal, and that's what we get, from the battery. But those, pushing, right? Remember, we talked about that in class. It's due to the chemical reactions inside the battery. That means, the battery has a lot of chemicals inside, and you do chemical reactions, which, basically convert some chemical energy into mechanical energy. Then those charges are being pushed from negative terminal to positive terminals, and that mechanical energy then converted to electrical energy. So there's a lot of things going on. So that's why it's kind of like it has a chemical energy, right? As a, you need chemicals to have a chemical energy converted to eventually to electrical energy. But here we have another, you can think of like another battery or another EMF source, but we're not using any chemicals here, okay? What we're using here is the, magnetic fields, okay? Magnetic fields and a conductor. Okay? The idea here is this. So for example, you have a rod connected to a stationary conductor. Okay, so you have a kind of like a U-shaped rod like this, okay? So it can kind of like extend if you want, And what you get here is you get the conductor. So this is our conductor, okay? And this conductor has, let's say, length L. That means it has a length L, right? Basically, and also it's not fixed, so it's free to move back and forth. So this point A and B, they're not fixed. They're kind of like connected to the conductor, right? Connected to that rod, but such that, you know, the conductor is free to move back and forth, right? So then here's then what we do. Okay, so for example, let's ask for a second, you know, ignore this, you know, like let's say, what we're gonna do here is this. Let's say consider this, you know, there's no current, nothing like that. If you have the conductor just sitting there at rest. So let's say initially the conductor is at rest. Okay. All right. So, and there's an into the page magnetic field. So there's an into the page magnetic field. Okay. But what I get here is this. Remember, this is, you know, that rod, right, is a conductor. So it has some charges, right? It's positive charges, negative charges, positive charges, negative charges, and they're randomly moving, you know, in random direction, remember? So kind of like a random motion. But here's then what I get, because, you know, it's a neutral, you know, conductor, right? So it has a bunch of negative and positive charges. So what I'm gonna do is then I'm gonna then take this rod and pull it to the right with some velocity. Okay, that means it's moving with some constant velocity to the right. Okay, that means, you know, what I get here is velocity is no longer 0, it is now moving. Well, as it starts moving, well, what I get here is, well, there's a magnetic field into the page. And if this conductor with those charges is moving perpendicular to that magnetic field, there is going to be a magnetic force acting on those charges. Let's use our right-hand rule to figure out in which direction will be the force. So if I take my fingers in the direction of the velocity, and I curl in the direction of magnetic field, which is into the page, I get upward force on a positive charge and a downward force on a negative charge. That means what I will get here is this. So there's going to be a force, let's say upward, right, if it's a positive charge, and downward if it's a negative charge. Well, that means all the positive charges are going to be pushed up towards point A, all the negative charges are going to be pushed down toward point B. What do we get at the end? Well, I get all the positive charges accumulated here, all the negative charges accumulated over there. That means my conductor basically become polarized, right? It's separated into positive and negative ends. Well, if that's the case, then what I will get here is then, you know, electric field. And the electric field is going to be in this direction, right? So it's kind of going to go like this. Well, if there's a, that means, and what I get here is, there's now I get EMF source because I get positive and negative, right? So that means what I get here is then delta V. There's a potential difference between those points A and B. Well, in that case, then if there's an electric field counterclockwise, right? That means there's going to be then a current counterclockwise. Okay, that means by moving this rod to the right with some velocity, what we get here is we get a current running in our, you know, in that loop. Okay, and EMF, which is then the potential difference between those points A and B, is directly proportional to the velocity, right? Because what we get here is the, you know, if no velocity, if that rod is not moving, there is no EMF. Only after you start moving, those charges start separating. So EMF is directly proportional to the velocity. But also, you know, if there is no magnetic field, there will be no, let's say, EMF. Also, what we have here is this conductor has to have length L so that the charges are separated. So it's also directly proportional to the length. So that we get here is this equation. So this is, again, it's an EMF source, but this is not a chemical-based EMF source. This is known as a motional EMF, where the conductor, you know, length, velocity, and magnetic field contribute into giving you EMF. And obviously what you get here is the magnetic field and velocity, they have to be perpendicular to one another, right? If the velocity is in the same direction as the magnetic field, you get no force, you get no separation, okay? That means this equation assumes that there's an EMF source. That means you're going to have a, you know, potential difference between points A and B, and the current running through that if you have a moving conductor. That means, for example, if I put a light bulb over there and move the conductor, the light bulb will basically receive energy from the system and be able to generate, electricity, right? It'd be generate light, okay? Because there's going to be a current going through that. What happens if you, let's say, move this conductor, in opposite directions? Let's say if you move it to the left, well, that means, it's going to push the charges in the opposite direction. This is going to be negative. This is going to be positive. And then the current will then switch the direction, right? In that case, the current will be clockwise, okay? But still, what you still get a current, but this time clockwise. So any type of device, right, a light bulb or something like that, will still be able to operate, okay? So that's why it's interesting, because you get, a motional EMF. So you take a conductor, move it in a magnetic field, you can generate, electricity. All right, so let's look at this example here. So here we have basically same setup. So you have kind of like a U shape, like let's say a system where there's and obviously that U shape is also all conductors, like this part where there's a, let's say resistive conductor, right? So there's a little bit of resistance there. So, and this is our rod, which is, free to rotate, free to move. And there's an into the page magnetic field, okay? And L is the length of that. So in the figure, let the magnetic field strength to be 0.8 Tesla, the rod speed to be 10 meters per second, and the length to be 20 centimeters. The resistance of the resistor then 2 ohms. All right, so the resistance of the rod and the rails are negligible. All right, so then find the induced EMF in the circuit. Let's do one at a time. So find the induced EMF in the circuit. Well, induced EMF is V times B times L. Well, it's simple enough. If I have a velocity perpendicular to the magnetic field, which I have, and I have the volume for that, which is 10 meters per second, and I have the magnetic field strength, 0.8 Tesla, and the length of the rod, 0.2 meters, and I can calculate then magnetic, motional EMF to be 1.6 volts. And it's a reasonable, relatively decent, potential difference, like a, AA or AAA battery, right? 1.5 volt, this is 1.6 volt. That means if there's a light bulb there or something like that, it will work perfectly. All right, so part B says, what is then the induced current in the circuit, including direction? Well, remember, one of the things we can do here is, since I have the EMF and I have the resistance, excuse me, then I can use Ohm's law. EMF equals current times resistance. All right, that means from here I can calculate induced current, taking EMF and divide by resistance. So 1.6 volts divided by 2 ohms. So we get 0.8 amps. Right, it means 0.8 amps of current. All right, we got that as well. Well, the next it says, what is the force needed to move the rod with constant speed? All right, so this is different. So this is not the force that I was talking about that moves the, let's say, the charges separates inside. This is going to be the force that, generated on the wire, right? Generated on the wire because of the external magnetic field. I remember we talked about before the force on a, let's say this conductor is going to have a current running through that, and there's an external magnetic field. I remember the force on a wire was ILB sine of theta, right? We talked about that in chapter 20, right? Because of the, magnetic field exerts force on that wire, okay? All right, so then what we get from here is, since the L and B are perpendicular, so it just becomes I times L times B. So this is then 0.8 amps times 0.2 meters, and then 0.8 Tesla. Then the force will be then 0.113 newtons. Okay, so multiply those three things, so you get 0.13 newtons. All right, so part D, it says find the power delivered by the force found in part C. Well, remember, what is power? Power is some energy per unit time. So then why do we generate or the, let's say deliver power? Well, when it says deliver power means that, okay, so find the amount of energy transferred into the system when this force is doing work, right? So now, one of the things we can do here is to find power. If you remember, if you know the amount of force that you exert and the velocity of your system, then power equals velocity times force, or force times velocity. This is one of the equations of the power. Remember, power is energy over time, but let's say this is also can be converted into force times velocity. All right, so force was 0.13 newtons, velocity was 10 meters per second, and I can calculate this to be 1.3 watts. That means this is the amount of power delivered. That means the amount of energy per unit time delivered. So this was, all right, so this was part A, this is, sorry, A, B, C, and this is part D. And I also have part E, which says, now, let's say that 1.3 watts is delivered to the system, but then how much energy or how much, the rate at which of joules heating in the resistor? It means what is the power of, energy dissipated by the resistor? It means I can, remember it says, when it says the rate, that means it's considering, change in, or rate of joule heating means that the amount of energy dissipated by the resistor as a function of time. That means power of that resistor. Well, remember, we talked about that power of the resistor is current times, EMF, right? Or it could be current squared times the resistance. Or it could be, let's say, EMF square over the resistance. Any of those equations is going to give you the same thing. So let's say, for example, if I do, current square, which is 0.8 amps squared times 2 ohms, to calculate this, I'm going to get then 1.3 watts. Then why 1.3 watts? Because, the resistor always dissipates, if it's just one resistor, so how much is delivered is exactly equals to how much is dissipated by the resistor, right? That means, what you have here is you have just one device. How much power you give it to your device, to your system, basically if it's just one device, you just take all that energy and dissipates it. All right. Okay, so the next we're going to talk about what we call, mutual inductance. So let's say then you can think like some of the applications of this. All right. So we have mutual inductance, and we're going to talk about self-inductance. So this is, actually something that you might have noticed, not necessarily understand that this is an application of the, let's say, inductance. So whenever you, move toward the traffic light, especially, let's say at night, sometimes you might see that the light changes. So you can see, right, many traffic lights change when car rolls up to the intersection, especially at night when you just know not a lot of cars. So you see there's a red light, you approach the traffic light, suddenly changes to green. Okay. So this process, you can see, right, works because a large coil is placed under the street, which carries a current that changes with time. Well, remember, one of the things we can do here, we just learned that, the moving car, right, in a magnetic field, moving conductor in a magnetic field can generate, current. So the car contains conducting material. So when it is near the coil, electric currents are induced in the car, which in turn induce an EMF in the buried coil. All right. That means you have a couple of things. So the car contains induced material, which is, when it's near the coil, electric currents are induced in the car. Okay. And so there's a kind of constant magnetic field, but as you're moving in that magnetic field, you generate current. And as the current goes, through your car, it's harmless for you, but let's say as the current goes, through your car, that current, since remember, so that basically you go from no current in your car to some kind of maximum amount of current in your car. That means you have a change in current in your car. That generates magnetic field of its own, and the coil under the, let's say concrete, right? So basically there's a coil over there, the magnetic field generated by your car that is changing through that coil, that makes that coil induce its own magnetic field, its own current, and that basically signals the, the traffic light. So that's why all this is, application of a, inductance. So you induce current by just simply, moving your car through that, let's say, external magnetic field and all those things. So, all right, another, thing like this. So another way of looking at it is things like this. So mutual inductance means that you have two things, right? Two coils. One was the car, the other one was the coil buried underneath, right? And they have to work together in order for the system to work. That means you need two neighboring coils of wire. All right, so let's think like this. So you take two general wires. So let's say here's coil 1. So coil 1 has N1 turns, okay? And what we do here is this. So if the current in coil 1, so you can see, right, coil 1 has to be connected something. So coil 1 connected or has a way of having a current through that. But in this case, think like this. Coil 1 is connected to something. So then you have a current running through the coil 1. Well, if there's a current running through the coil 1, it generates a magnetic field. So those blue lines you can see, right, is the magnetic field generated by coil 1. And you can see, right, some of those magnetic fields go through the coil 2. So then you have flux 2. That means there's a flux through the coil 2. If the current 1 is constant, coil 2 is, not going to do anything. It's just going to sit there, okay? But if the current in the coil 1 starts changing, well, if you change the current, you are basically changing the magnetic field, right? And magnetic field through then coil 2 will be changing. So that's what we are looking at the case when the current in coil 1 changes. If the current in the coil 1 changes, then those magnetic field lines through the coil 2 will also change. Well, if the magnetic field is changing through the coil 2 going to induce current, right? And it's going to induce its own magnetic field. So that's kind of the idea. That means changing current 1, right? If you change current 1, this induces an EMF in coil 2. And as the coil 2 now has its own current, it's going to generate its own magnetic field, which is going to go through the coil 1, and then it's induced magnetic field over there. So you can see it kind of goes back and forth. So this proportionality constant for this pair of coils is called mutual inductance M. That means this mutual inductance is, amount of, let's say, change in the magnetic flux through the coil 1 and coil 2. That means by changing magnetic field through the coil 2, you're inducing, a flux over there or inducing current over there. And that current in coil 2 generates magnetic field that then goes through the coil 1. And if that also changes, then the coil 1 generates its own thing again, and so on and so forth. So that's why. All right, so then what we get here is this mutual inductance, okay, is, again, is kind of like, let's say, equals to the, so this is for, you can think of like, let's say, so you can think like mutual inductance for the coil 1 is equals to the mutual inductance of the coil 2, okay? So that means the mutual inductance, this quantity that we're going to calculate, is same for coil 1 or coil 2. So that's why it's called, it's a constant, or proportionality, constant. All right, so then this is equals to, so let's say you're talking about, for example, you can see, right, this is for the coil 2. So let's say what you do here is you take number of turns in coil 2, okay, times then the flux through coil 2 divided by, so whatever basically gives you the change in that, let's say, particular, coil. And then remember that what you get here is that this is due to the, current in wire 1, right? If you have you can see, right, the current here is written as, lowercase because we can assume that it's a changing current, right? So that means, if you have that, the current will be changing, then there will be, change in flux. So a similar way, you can look at it in terms of coil 1 and say that, all right, so then number of turns in coil 1 times the flux in coil 1 and divided by the current 2. Okay, so that's kind of like what we get over there. That means mutual inductance you can calculate in terms of the, coil 1 or coil 2, right? So in a way, what we get here is this. Number of turns in coil 2 times the flux in coil 2 times the current in coil 2 equals number of turns in coil 1 times the flux in coil 1 times its current. And that is, equal. So that's why this equation, you just divide both sides by the current, and that's how you can find the flux. Okay. That means this is not the mutual inductance. Every one of those divided by then the opposite current, you can get that. But this one I just showing that those terms are also equal to one another. So let's say then you divide this one by, divide this one by I2, divide this one by I1, or both of them like that, and you get then the mutual inductance equation over here. All right, so the unit for the mutual inductance is called Henry, after Joseph Henry, who just like Faraday did some experiments in this. So then Henry is represent basically 1 Weber per amp. We can say, right, and its number of turns has no units, but it's flux divided by the current. So that's why 1 Henry is Weber per amp. Okay. But what we're going to see here is there's another equation for the mutual inductance, okay, and that will be in terms of then changing current. So remember, one of the things we have here is kind of, if I'm writing like this, right? See, mutual inductance is equals to N2, let's say, times flux 2, right, divided by current 1. Okay, so now remember the flux is related. So if, let's say, for example, if you're changing flux over time, remember, and times the number of turns, this was equals to EMF. Okay, see, now what I do here is, for example, if I multiply both sides by delta T, so what I get here is this. So then number of turns times flux is equal to the EMF times delta T. Okay, that means in a way, like let's say this guy over here, I can replace it with that, right? And that's what we're doing in the next slide. So I can get that equation. So you can see, right? So for example, in terms of what I have here is, if the M is equals to then, let's say, and put that out the equation, right? N2 times flux 2 over current 1, or N1 times flux 1 over current 2. So this is one equation that I can have, but also I can relate the mutual inductance to the EMF, right? Because remember, if I change that over time, change the flux over time, then I get EMF 2. If I change this over time, then I get EMF 1, and which is as a function of time. So then I can relate mutual inductance to basically that too. Remember, right? So if I take those two together, that two together basically is replaced with, the EMF times delta T, right? EMF times delta T. So then if I move this to the other side, becomes current times M, and divided by, delta T, move this over there too, becomes, changing current as a function of time times the mutual inductance, then equals to EMF. And that's what we get here. Okay. That means if you're looking at EMF of the coil 2, it's equals to mutual inductance times how the current 1 changes as a function of time. And if you want to find EMF for the coil 1 is mutual inductance, then times how the current 2 is changing as a function of time. Okay. Which gives you that basically the EMF generated by that mutual inductance. So one really nice application of that is also the electric toothbrush. The Sonicare, for example, I'm using. So what I have here is, so you have the, the base, right? So you can see that here's the base, and it's connected to a power source, okay? But then you have the toothbrush that is never technically connected. You can see there's no electrodes or anything like that. You just put it over there in the base. But what you have here, there's a coil over there in a toothbrush inside, and there's a coil over here. So as it's connected to the power source, then the current goes through the coil 1, let's say, and the coil 2, right? So as the current going over here, generates magnetic field through the coil 2. But the key here is that there's to be changing current as a function of time. And what we get here is, it is connected in all the appliances in our house, right? All those power sockets, right? They're actually not DC, but AC. An AC circuit, what it does, it changes the current. Our current as a function of time changes as fluctuates back and forth. And that means you have a changing current. Changing current gives you changing magnetic field. That means you always then can induce mutual inductance between toothbrush and then the base. So just pretty much put the toothbrush in the base, and it charges. It charges because of the AC circuit, which is the power outlet that you're connecting it, right? Constantly changes the current, which constantly induces current in the toothbrush. Okay, that's why the toothbrush doesn't have to be electrically connected to the base. Okay, it basically charges magnetically. Okay. All right, so let's look at then one example over here. You have two coils with a mutual inductance of 3.25 times 10 to the negative 4 Henry. The current I1 in the first coil decreases at the uniform rate of 830 amps per second. Okay, so let's see what we have. So we're given mutual inductance, 3.25 times 10 to the negative 4 Henry. And then we're given that the current is changing at that rate. That means what we get here is changing current as a function of time is equals to 830 amps per second. We can see, right? Current per time, so amps per second. Okay, so that's right. That quantity is the changing current as a function of time. All right, then what is the magnitude of the induced EMF in the second coil? Well, remember, that means I want to find EMF2. Well, this was mutual inductance with the constant, right? Then times changing current in coil 1 as a function of time, which was 3.25 times 10 to the negative 4 Henry, then times 830 amps per second. Okay. And if I do that calculation, right? By the way, one thing you can see, right? This could be negative, the absolute value, because technically it's negative because it's decreasing by that much, right? But this actually increases, but we're using absolute value. So if it's increasing or decreasing, it doesn't really matter. So then what we do here, we get 0.27 volts, which is about 270 millivolts. Okay. And is it constant? Yes, it is constant. Why is it constant? Because the current is increasing at the uniform rate. That means every second, 830 amps per second change. If that's the same, that means, because see, EMF doesn't depend on current. EMF depends on changing current as a function of time. And if the rate at which it's changing is uniform, that means EMF is constant. Right, part B says, suppose that the current described is in the second coil rather than the first. What is the magnitude of the induced EMF in the first coil? Well, if that's the case, remember then EMF1 is equals to mutual inductance times change in current 2 over time. Well, we still get the same 3.25 times 10 to the negative 4 Henry. And current change is same 830 amps per second. That means nothing changes. You still get the same, voltage as before. Okay. And again, still same constant EMF. All right. Now, the inductance. So basically, you can also have the circuit itself to, give you inductance. But here you have just basically any circuit, right? And because there's a coil right there, so let's say And this is, you know, you can think like this is a device called solenoid, right? So it can carry what we call self-induced EMF, okay? That means if you have a current, so you can see, right, here's our, you know, a power source, EMF, some, right? And there's a current going through that, you know, let's say usually it's a solenoid, right? Going through that. And you can see, right, it can actually do self-induced EMF. That means this device can induce its own EMF. Why? Because the current going through that device, so as the current going through that device, it tries to oppose it. Because remember, the current that going through the wire generates magnetic field. But the idea here is that the current increases as a function of time. Remember, as I said, right? When you, let's say if there's a switch here, when you close the switch, the current doesn't right away go to a maximum. The current, you know, takes a fraction of a second, but it increases from 0 to maximum. But as it, you know, as the current goes through those coils, it increases. The coil tries to oppose that change, and it induces its own, you know, magnetic field. Remember, how does it induce its own magnetic field? It has to induce its own current, and it induces its own EMF. So that's why it can do self-induced EMF. It can try to fight it for a little bit, right? But then as the current becomes steady, that, you know, the induced EMF technically goes to 0, you know, very quickly. Okay, but still, one of the things we can do here is you can have this device which kind of, what it does, it actually makes the current, this current from this, you know, the power source, right? It makes the current increase at a slower rate. That means one of the things you want to do here is, if let's say you want in your circuit current to increase, but not increase very fast, but increase kind of slowly, you can put that device, like basically like a solenoid or something like that. And what it does, it decreases the rate at which your current goes to maximum. Because sometimes some of the devices actually need a little bit of time to like warm up or something like that. So that's why, if I don't know, if you have a printer, right, sometimes you turn on your printer, it says it's warming up. That means, you know, you can't use it yet because it's, you know, the current in your let's say a printer is not at maximum, you know, let's say efficiency. Why? Because the circuitry and things like that is very sensitive, and you don't want the maximum amount of current to go through the circuit. Because what if there's a short or something like that, then you're gonna have too much current and it can destroy everything. So that means there's a solenoid that, you know, opposes right away the change in the current, and then it slowly increases the current to its maximum. Okay. Now, what is the value of this self-induced EMF? Well, we can use basically this capital letter L to define this, you know, self-inductance. And this self-inductance, kind of very similar. Remember, this is mutual inductance, which was, remember, N times flux divided by current. But this was for the, you know, you needed 2 coils, right? So this was number of turns in coil 1 times the flux through the coil 1 divided by current in coil 2. But, you know, this is for the mutual inductance, but this is a self-inductance. There is no 2 coils. There's just 1 coil. Well, that means there's still, it's still, you know, proportional to the number of turns, still the proportion to the flux, and inversely proportional to the current, but it's just 1 coil. So that means it's just, you know, there's no subscript, just N times the flux divided by the current in the coil. All right. And you still can calculate this induced EMF, which will be, again, same equation, which is inductance times the change in current over time. But if this was the induced EMF through the mutual inductance, which was dealt, you know, current I over, you know, change in I over T, right? Here you have then, this is for the induced EMF if it's a self-inductance. So this L is representing this self-inductance, or sometimes just inductance, okay? So this one is always mutual inductance, but when we say inductance, we usually mean self-inductance, especially in the circuit. Okay, that means try to understand the difference between self-inductance or just inductance and mutual. For the mutual, you need 2 coils. For the self-inductance, you need just, you know, 1 coil in the circuit. All right, so let's look at then this last example that we have. At the instant when the current in an inductor is increasing at the rate of 0.064 amps per second, the magnitude of the self-induced EMF is 0.016 volts. Okay, so what we given here is some kind of circuit maybe, And there is, generally this is how we represent inductance in the circuit. So L. So what we're given here is we're given the value of the inductance as we're not given the value of the inductance. We're given the, EMF, right, for the self-inductance, 0.016 volts, okay? And we're given how the current changes through that as a function of time, which is 0.064 amps per second, okay? So what we want to calculate is what is the inductance of the inductor then? So what is this L? So what is the value of L? Well, one thing we know, there is this inductance EMF, right? EMF, that means the potential difference between those two ends of the, inductant. Because most of the time this inductor are solenoids. Inductor is just like a capacitor or a resistor. It's a device, but like the shape a lot of times is a solenoid, just like the capacitor, right? You can have a parallel plate capacitor, or you can have spherical or cylindrical capacitor. So capacitor is a device, but you can have different geometry. But in any case, so then EMF is equals to then inductance of the inductor times then changing current over time. Okay, so I can rearrange this where I can find the inductance by taking EMF and dividing by this, the changing current over time. Okay, so divide both sides by that. Okay, so I get 0.016 volts divided by this quantity changing current over time, which was 0.0640 amps per second. Okay, then I calculate this for the inductance, I plug in the values and just calculate this to be 0.25 Henry. All right, again, using this general equation that relates inductance to the EMF and changing, current rate. All right, so part B, it says, if the inductor is a solenoid with 400 turns, what is the average magnetic flux through each turn when the current is 0.72 amps? All right, so now, one of the things we have here is then I can, since I'm given number of turns, right, for part B, I'm given number of turns as 400, and I'm given that, there's a current of 0.7, or, you can write kind of like this, right? This is at some instant, right? 0.72 amps. Then obviously now I have the inductance of 0.25 Henry. What is then the magnetic flux? Well, I have another equation that relates all of those quantities by, N times flux divided by the current. So I just rearrange this and I can calculate the flux, which will be L times I, then divided by number of turns. So 0.25 Henry times the current of 0.720 amps divided by number of turns, which is 40. So now I calculate the flux to be 4.5 times 10 to the negative 4 Weber. All right, so that's then the magnetic flux through the, let's say, through that solenoid, okay? And this is kind of like the average, so that means, obviously sometimes it's more, sometimes it's less, but this is kind of like the average magnetic flux. All right, guys, so that's it for this chapter. So make sure you guys start working on the homework problem for chapter 21. So we are basically, more or less concluding this, magnetism. We're going to talk about AC circuits in next chapter, right? But next chapter is kind of short, so I should be able to, maybe make a video and upload it again, sometime this week. All right.